All right, everyone, we're gonna finish up lesson 13, electron configurations. I stopped earlier last time because it was getting kind of long, and so I wanted to break it up. So let's go ahead and finish up electron configurations now. So if you'll get out your study guides and turn to lesson 13, and we'll just pick up where we left off. All right, so what I want to remind you is that you should have already filled out the orbital diagram for several elements and have also completed the electron configuration for those elements. I want to remind you about some important ideas about electron configurations before we continue with the rest of our notes. So remember, when we write an electron configuration, we always put the energy level that the subshell is going to be on first, followed by the subshell, whether it's an S subshell or P or D or F subshell. And then the superscript is going to be the number of electrons that are found in that subshell. All right. And then let's go from there. All right. So this is where we're at in your notes. You have this page where it has some elements, and then where it says electron configurations, and then a condensed electron configuration structure, okay? So we're gonna fill this out, and I'm gonna show you essentially how to quickly determine the electron configuration for any atom, just by using a periodic table, okay? So I'm gonna go back to a periodic table, and you can follow along with me as we do this, all right? So first of all, you must remember that we divide the periodic table into blocks, right? So this is the S block, in the middle is the D block, this is the P block over here, and down here is the F block, okay? So by knowing those blocks, this will help us to determine the electron configuration for an element pretty quickly. Also remember that the period number is also the shell number, so, or energy level. So 1, 2, 3, 4, 5, 6, and 7, okay? So these ideas are what we're gonna focus on, okay? So on your sheet, if in fact, just let me turn to it, my study guide, so I can follow along with you. The first element is helium, okay? And then you have basically a blank line there that you're gonna fill in the electron configuration for, okay? So I'm just going to do it right here, work out the problem where I have the periodic table and where I can show you how to use the periodic table to figure out the electron configuration of helium. Okay, now remember that we actually put helium right here, He, when it comes to electron configuration in that S block. Okay, so what we're going to do is we're going to count everything up to helium. So we're going to start with the first energy level. So we got 1. That's the first energy level. And then we're in the S block, or the S subshell. So I'm going to go ahead and put an S. And then the number of electrons, remember each box represents an electron. So we're going to count the number of electrons per box. So 1, 2, and we're at helium. So we're done. So then I'm going to put a 2 up here. And that's it. That's the electron configuration for helium, okay? So 1s2, okay? So again, I'm just counting using boxes representing 1 electron, the block S, P, D, F blocks on the periodic table, and the period number for energy levels, okay? So let's do beryllium. That's next on your paper, okay? And again, you got a line here. And I'm only focusing on the first column, by the way. We'll get to the second column later. So for beryllium, we know that it's on the periodic table. It's right here, right? So that's 1, 2. If we're counting helium block here, 1, 2, 3, 4. Okay, so we have 4 boxes of 4 electrons. So we're going to start with the first energy level. So I'm going to put my 1 there, and we're in the S block to start with. So 1s, and the S block is filled by 1, 2 electrons. So far beryllium is 1s2. And then we go to the second energy level. So I'm going to put a 2. We're still in the S block for lithium and beryllium. So I'm going to put an S and then count the number of boxes, 1, 2. And so 2 electrons. So for beryllium, its electron configuration is 1s2, 2s2. Okay. Now let's do carbon. That's the next element there. So, where's carbon on the periodic table? It's right here. So that's where we should end with. So it looks like it ends in the P block. So our last thing we should write is in the P subshell. Okay. So let's take a look. We're going to start here at hydrogen, and we have 1s1 for hydrogen, and then 1s2 for helium. And then we go to the second energy shell, and we're in the S block again. And for lithium, it would be 2s1, and then beryllium is 2s2. So that fills that subshell. So then we jump all the way to the P block, which starts here at boron, and we're still in the second energy level. So it's going to be 2p. Boron is 1, carbon is 2, so 2p2. So there's the electron configuration for carbon: 1s2, 2s2, 2p2. Okay. Let's see, neon is next. Neon. Okay, so neon is right here in the periodic table, right? So that's where we need to end. It looks like we end in the P block still. So we're going to start out with beginning 1s1, 1s2. So 1s2. And then we go down to lithium. That would be 2s1. And then beryllium is 2s2. And that fills that subshell, 2s. So then we go over to the 2p block. So this is 2p1, 2p2, 2p3, 2p4, 2p5, and then finally 2p6. 2p6. And there we go for neon. Okay. And if I need to box the electron configuration or the valence electrons, I can do so. So here are the valence electrons, right? All right. Calcium is next. All right. So where's calcium on the periodic table? Should be right here. So we need to go to the 4s. Wow. Okay. So let's do this. So we're going to start with 1s1, 1s2. Okay. So 1s2. And we go to the second shell, and for lithium, it's 2s1, beryllium 2s2. So again, we're just kind of going in order. And then we go to the P block, and this is the 2p1, 2, 3, 4, 5, and 6. So 2p6, right? We filled that up. So now we go to the third energy level, and we're going from 3s1, that's sodium, 3s2 is magnesium, and that fills up the 3s subshell, 3s2. And then we go to the 3p, that starts with aluminum, and that 3p1, 2, 3, 4, 5, and 6. So 3p6. And then we go to the fourth energy level, and remember we're going to calcium, so 4s1 for potassium and 4s2 for calcium. So we're going to end at the 4s2. And there we go. And this is our valence shell, 4s2. Okay, so hopefully you're kind of seeing what's going on here as we do so. I'm going to clear everything here. And let me go to our next element, which is scandium. Okay, scandium. Okay, and I'm going to start here at hydrogen and helium. So that would be 1s2, right? And then lithium and beryllium would be 2s2. Okay, and then boron starts the 2p all the way to neon is 2p6. Okay, and then from sodium to magnesium, that would be the third energy level, s subshell, 2 electrons in that, and that's filled. Okay, so then we jump to aluminum, and that starts the 3p's. So from there to argon would be 3p6. And then we go to the fourth energy level, potassium and calcium would be 4s2. Okay, and then we get to our target element, scandium, right there. And scandium is a transition element, so we're going 1 electron shell back to the third energy level. And since this is the D block, it's going to be D1. Okay, so there's your electron configuration for scandium: 1s2, 2s2, 2p6, 3s2, 2p6, 4s2, 3d1. Now, what's the valence shell is the 4s2, okay, not the 3ds. It's on the third energy level, so the 4s is our valence shell. So we have 2 valence electrons there. Okay, awesome. Okay, what's our next element that we need to do? That is titanium. Okay, so titanium can be very similar to scandium since they're right next to each other. So it should have essentially the same electron configuration: 1s2, 2s2, 2p6, 3s2, 2p6, 4s2, and then 3d2, titanium. Okay, since titanium is right here on the periodic table, it has 1 more electron in the 3D. Okay. All right, what's next? Zinc. All right, so let's do zinc. Getting more here. So zinc is right here. So we should have everything here from 1s, so the 1s2, right? 1s2, then 2s2, 2p6, 3s2, 2p6, or sorry, 3p6. That's 3p6. Maybe I better do a better job here with that. Okay. 3p6, 4s2, and then we're to the 3ds. Now, how many Ds? Well, we're going all the way to zinc, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Zinc is my last transition element in the D block. So it should be 10 there. Okay, so there's zinc. All right, what's after zinc? Gallium. Okay, Ga, gallium. So let's see if we can figure out gallium. It's right here on the periodic table. All right, so it's going to be 1s2, 2s2, okay, 2p6, 3s2, 3p6, 4s2, 3d10, okay? So we're at zinc, that's where we left off. And now one more. Now we're at the D block, and this is the P block, right? So gallium should be a 4p1, right? And that should be gallium. So right here, 4p1, it's in the fourth energy level or the fourth period in the P block, so 4p1. So the valence electrons would be the 4s and the 4p. So not the 3d. All right, so there's gallium. Wow. All right. All right, now we got some ions. Okay, now when we share some things about the ions, remember that we either lose or gain electrons. So that means that we're going to have to count for that. So the first one is sulfur 2 minus, okay? That means it's gained 2 electrons. So what I would normally do is write the electron configuration for the non-ion version first, okay? So if we were to do this really quick, it would be 1s2, 2s2, 2p6, and then 3s2, and then 3p, oops, 3p, let's count. So we're right here, 3p, 1, 2, 3, and 4. So we end with 3p4. This would be the non-ion form of sulfur, the neutral form, okay? But since it's gained 2 more electrons, where are we going to put those electrons? Well, the energy level that's in the valence shell is where we're going to start adding, okay? So the S, the 3s is already filled, so it would be the 3p that we would add those electrons. So I will get rid of the 4, right? And add 2 more electrons to make that a 6, okay? So that means that I have a valence shell of 3s2, 3p6. Now, if I gain 2 more electrons, I have an electron configuration that is exactly the same as argon. So sulfide or sulfur 2 minus has the same electron configuration as argon, okay? Now, are they the same element? No. Sulfur still only has 16 protons in the nucleus, whereas argon has 18 protons, okay? They're not the same element. They're different, but they do have the same electron configuration. So if 2 atoms, write this down because this is super important. If 2 atoms have the same electron configuration, they are known as being isoelectric to one another, okay? Isoelectric, okay? Isoelectric. So isoelectric by definition means that 2 atoms that are different from one another has the same electron configuration, okay? So we would say that sulfur 2 minus is isoelectric to argon, okay? All right, let's go on to some other ones here. Let's do sodium ion, okay? So Na plus. So because it's a +1, that means sodium's lost 1 electron. So again, I'm just going to go ahead and draw out the electron configuration for just neutral sodium, okay? So that should be 1s2, 2s2, and then 2p6, and then 3s1, okay? So this would be just regular sodium, okay? 1s2, 2s2, 2p6, 3s1. But we're looking at sodium with a +1 charge, so it's lost 1 electron. Where are we going to lose that 1 electron? Remember, we start with the valence shell first, okay? We always will lose electrons from the valence shell, okay? So we'll go from the outer shell, valence shell, and work our way into the core electrons. So our valence shell is the 3s1. So that means we're going to lose this 1 electron. So I'm going to lose that whole valence shell. It's going to go bye-bye. And what do I have? I have an electron configuration of 1s2, 2s2, and 2p6. And that is our new electron configuration for the sodium ion. Lights went out again. Sodium ion, okay? Whoa, all right. So sodium has the same electron configuration as neon. Wow, or sodium ion, Na plus, has the same electron configuration as neon, okay? Which means that sodium plus and neon are isoelectric atoms. They have the same electron configuration, even though they're still not the same atoms, okay? All right, so this is really likely when ions are formed, is that they're going to be isoelectric to some other element, often to a noble gas, okay? All right, so what do we got? We got aluminum, Al, 3 plus, all right? So again, we have an ion, it's lost 3 electrons. So I'm gonna take and draw the electron configuration for just neutral aluminum. So that's gonna be a 1s2, a 2s2, okay? Then a 2p6, 3s2, and a 3p1, okay? That's neutral. There's the valence shell, okay? Neutral aluminum, but it is an ion that's lost 3 electrons. So where are the 3 electrons going to be lost from? Well, from the 3p and from the 3s, the valence shell. So those 3 electrons are going to go bye-bye. And what do we have left is 1s2, 2s2, 2p6, okay? Oh, wow. Guess what? Aluminum is isoelectric to neon as well as our sodium ion, okay? All 3 of these elements are isoelectric to one another. They all have the same electron configuration, okay? So don't forget that, okay? Now, what do we have? Chromium and copper. Oh, okay. Now, chromium, copper. Now, sometimes there are some exceptions on the periodic table to the electron configuration that doesn't normally fit in our normal pattern. And chromium and copper are going to be 2 exceptions that you need to know for the AP or IB exam, okay? So let's start with chromium first. All right, now the normal electron configuration you would think, all right, this is what you would think chromium would be, okay? You would think that it would be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2. Okay, so this is where we're at. We're at calcium right now. And then we go to 3D, and then we would count 1, 2, 3, 4, okay? Now, this is what we would normally think, okay? And that is because we would think that the 4s is going to be, you would think, lower in energy than the 3Ds. Okay, so then we have 3Ds. All right, and so you would think you would have electrons that look like this. All right, so this would be the orbital diagram for chromium and those last electrons. Okay, this is the way you would think. Okay, because we have said that in most cases the 4s is lower in energy than the 3D. But this is not going to be the case for chromium. Now, I'm not going to go into all the details why that is, okay? Why this is not going to be the case for chromium. In reality, the 4s and the 3Ds, 1, 2, 3, 4, 5, the 3Ds are all going to be identical in energy, okay? So in reality, what's going to happen is we're going to follow Hund's rule, and we're actually going to take these two electrons and these electrons and put them in the 4s and 3D following Hund's rule, since they're equal in energy. So the 4s and the 3D, 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 and 3D, okay? So these are 1, 2, 3, 4, 5, 6 electrons, which represents the 6 electrons right here. 1, 2, 3, 4, 5, 6. Okay. So this is the real orbital diagram. This is the true orbital diagram for chromium. Okay. So it really puts the electron configuration for chromium as 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1, right? 4s1 and 3d5. Okay, so this is the real electron configuration for chromium, or the exception to our rule that you need to be aware of and know. Okay. Again, I'm not going to go into all the specific details of why that is. It has something to do with, again, we want to put electrons in the lowest energy state possible. And in this case, this is the lowest energy configuration for chromium. Okay. All right, so now we're going to go to copper. So copper, we might expect the electron configuration to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, and we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9. This is what you might expect the electron configuration for copper to be. And so that is because, again, we would think that the 4s is lower in energy, 2, 3, 4, 5, than the 3d. So that you would have electrons in the 4s and then in the 3d, like so. Come back, fill those in like this. This is what you would think, okay? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? However, this is not correct, okay? The real thing is that the 4s, again, in the 3D, 1, 2, 3, 4, 5, are very similar to a certain extent in energy, okay? So we're going to fill in 1 electron there, 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 and 1 electron there, okay? So that's going to be 1, 2, 3, 4, 5, 6. Then we're going to go back 7, 8, 9, and then, oops, sorry, I did one thing wrong. We need to do the D's first. I made one mistake. We should be doing the D's first. Okay, we need to do the D's before we fill up the 4s, okay? Because the 4s is actually a little bit higher in energy. So we're going to fill this up here and then into here. So the 4s is just maybe slightly higher in energy than the 3D for copper. And so we're going to have just this half full. So kind of maybe I should draw that a little bit different. I apologize. I think it'd be better to show the 4s. Actually, the 4s to be a little bit higher in energy. So there we go. The last electron would go there. So the 3D would be filled first and then the 4s. So the electron configuration for copper would be essentially 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p6, 3d10, and then 4s1, okay? With that being the valence shell. So this is the real electron configuration for copper, okay? And again, I guess you could say that the 3Ds are lower in energy than the 4s, okay? And so the 3Ds are going to fill up first, and then the 4s will be filled up after, okay? And again, why the 4s is higher in energy than the 3D, we're not going to get into the details. Again, we're just creating an electron configuration structure that gives these electrons the lowest possible energy state in the atom, okay? So there are other exceptions in the periodic table, but these are the two that you need to know for the AP and IB exam, is chromium and copper, okay? Let's go back and re-look at that if you need to. All right, so there's our notes. We've kind of filled everything in that you need to look at. The only other thing is that last column. So this last column here, or the second where it says condensed electron configurations. So let me kind of show you what the condensed electron configuration is, and then we'll kind of in from there, okay? So helium does not have a condensed structure, as you're going to find out. So if you look at beryllium, it has a 1s2 and a 2s2 structure. So what we're going to do is we are only going to show the most important electrons in the atom for the condensed electron configuration. So that would be the valence electrons here, the 2s. So what we're going to do is we're going to take everything up in front of the most important electrons, and that electron configuration in front should be the representation of a noble gas. So the 1s2 is a representation of helium. So we're going to actually put helium in brackets to represent our 1s2. And then we're going to just put 2s2, and that is the condensed electron configuration. All right. For carbon, let's show you it's 1s2, right? 2s2 and 2p2, right? So what's important is these valence electrons. So again, we would go helium, and then we would just put 2s2, 2p2, and just show that, okay? So let's skip down to scandium because you can do the rest of these. So scandium, would be 1s2, 2s2, 2p6, 3s2, and 3p6, 4s2, and then 3d1, right? So these ones right here are going to be my most important electrons at the end. The 4s being in the valence shell, and then the 3d1 we want to include. So everything here is the electron configuration of a noble gas. Well, what electron configuration for which noble gas? So if you look at your periodic table, it should be the electron configuration for argon. So I'm just going to take argon and put it in brackets, and then I will put the 4s, 2, and 3d1, and that's the condensed or abbreviated electron configuration, all right? And only including those most important electrons at the end there, okay? So you can go back and you can do that for all the other ones, and just write the condensed structures for the electron configurations. So just take the nearest noble gas of the configuration in front of those valence electrons, and then, oh wow, you got it, right? Try it, okay? Well, I think we're going to conclude here for today's lesson. So that includes electron configurations, and yeah, study your notes, and I'll see you later.